Well, in this second section of the second part of the course about vibration, mechanical vibration, I talk about the second order oscillatory system. It's a second order system with complex poles, and this is all material that has been tackled in previous courses, for instance in the digital control course, but also in the state space control course. So I will be very brief and I will not go into the details. As a first example of a harmonic oscillator, we consider the mass spring system, and if we write down Newton's second law, we know that mass times acceleration is the sum of the forces. You have the restoring spring force, you have the damping force, and you have the external force. So if you go to the Laplace domain, so you have y of s divided by f of s is equal to 1 over m s squared plus c over m s plus k over m. This thing here we'll call the natural frequency squared, and this yields this equation. And c over m, we'll write it down as 2 times zeta omega n, and here this is the damping ratio. So the damping ratio can be written as 1/2 c over m divided by omega n, so that's square root m over k. So indeed we obtain that the damping ratio is given by this equation, right? So now we have written a transfer function from f to y in this way, but we like to write it in this fashion because this transfer function here is kind of the canonical form of the harmonic oscillator, because it has a gain of 1. And you see that if you plug in s equals to 0 in here, you have 1. This is divided by this, it gives you 1, and this has indeed a static gain of 1. So you see that the static gain of this system is 1 over k. Well, here you have a second example of a harmonic oscillator, which is the pendulum, and again we'll write down the second law of Newton, but this time in rotation. Then you have the moment of inertia times phi double dot, and this is a point mass here which is rotating at a distance L from the point of rotation. So indeed the moment of inertia is m times this distance squared. So J, moment of inertia, times phi double dot is equal to the sum of the torques, which is the net torque. There is of course the external torque, which you've got over here, and then 2 other torques, one that is related to friction, the friction torque, and one that is related to gravity, and we have to take this component here of gravity, which is mg sine phi times the distance L over here, and then we have the counter torque which comes from gravity, and we have the equation of a pendulum, right? Well, this is a nonlinear equation, and we use the usual approximation for small angles. You say, well, sine phi is approximately phi for phi very small, and you obtain this equation here for the pendulum. Okay, so we can do the same thing that we did for our mass spring system. We can take this equation and go to the Laplace domain. So what we'll have here is phi s divided by ts, which are the Laplace transform of phi of t, and this one is the Laplace transform of my external torque, and we'll have something like 1 over ml squared. We'll have s squared. Then here we'll have c phi divided by ml squared. You have noticed that I have divided everything here by ml squared plus g over l. So this is our natural frequency squared. So this gives us this expression for the natural frequency that you know very well. And then you have that this term here, you write it down as 2 zeta omega n, and this is c phi ml squared. You know that this one is given by this expression here, so zeta is 1/2 c phi over ml squared, right, and then divided by omega n, and this gives you this expression over here. So we have now obtained this expression, and just as before, we prefer to write it in this way here because we have the expression of the canonical equation for a harmonic oscillator, and here we have the static gain of our process. Okay, so here's a third example of a harmonic oscillator, which is an example of a floating body. Again, we can write Newton's second law. Mass times acceleration is the net force. So you have gravity that is acting. We assume that there is a damping force, there is an external force acting, and there is also the buoyant force, which is Archimedes' force. It corresponds to the weight of the displaced volume, and we assume here that this volume that is displaced is a volume of water. So the volume is A times X times the density times G. Okay, so you obtain your equation of your harmonic oscillator. This term is kind of annoying us, so we are going to rewrite things a little bit. We know that in steady state, when the transients have gone, mg is compensated by the buoyant force. So we have this thing here, and I'll rewrite it x steady state, right? So this one I can take out, and this is how you compute the steady state value of x. So oh, it's not here, it's over here. This is this equation here. So now we are going to rewrite the equation using a variable y, which is the position x minus its steady state value. And if you do that, this term will compensate out, and you end up with this equation of the harmonic oscillator. Well, here is our equation of the floating body, rewritten using this y variable, which expresses the fact that you're looking at the movement around the steady state solution. If we go again to the Laplace domain, you can write things like this. I divide by m, so I'll have 1 over m s squared plus c over m plus over m. Forgot to write my s over here, so this as usual will be defined as the natural frequency squared, and this gives you this equation here, right? But this thing here we can write it differently, because this quantity here, well, you can write it as 1 over x steady state, right? So one way of writing the natural frequency is like this, and then c over m, well, we write it as 2 times zeta omega n. So zeta, the damping factor, is 1/2 C over M 1 over the natural frequency, which is written like this, and this is indeed what we obtain, right? So this is the transfer function that we have obtained. We would like to write it as usual using the canonical form of the harmonic oscillator, okay, because it has a steady state of 1, and then we have to adapt things a little bit to take into account that we have taken this term over here, and we obtain here the static gain of this particular system. Well, in the previous slides we have seen examples of systems, harmonic oscillators, that can be written under this form with an additional gain k of p, right? So it's very important that we are able to analyze this system and this second order oscillatory system, and this is a system that you know very well, as I've said before. We are going to consider it in the case where zeta is between 0 and 1. Zeta is the damping ratio, and in this case, well, the poles of that system will be complex and the system is called underdamped. The other quantity that you know is the undamped natural frequency omega n. Well, this thing here, as we have seen in the course of signal processing, you can write it down by completing the squares, and you can complete the squares using these two first terms here. And as you can see, well, if you want to complete the squares using these two first terms, you should take S plus zeta omega n. Indeed, when you're going to square that, you're going to have S squared and 2 zeta omega n. Okay, when you complete the squares, you see that you have taken a little bit too much, okay, and this is why you have to subtract the square of this one, which is zeta squared times omega n squared. So this notation over here is totally equivalent to this one, and we'll call this one sigma, and we'll call this thing here omega d squared, and this is what is called the damped frequency. Okay, from here it's very easy to see that the poles of the systems are given by this expression over here, and when zeta is in between 0 and 1, you will see that indeed these are complex poles. When zeta is larger than 1, you have a completely different response. For instance, when zeta is equal to 1, you can see very easily that this will be S plus omega n squared. Okay, this is under the assumption that zeta is equal to 1, and then you have a double real pole. If zeta is larger than 1, well, the poles will be real but different. Okay, and this type of response is very different. For instance, when zeta is larger than 1, you have what is called an over damped response, and this type of response, of course, is not really relevant in this course where we talk about vibration. So we can have a look at the impulse response in the case of interest, and with zeta smaller than 1. Then of course the response of the system y of s is equal to p of s times x of s, and for an impulse response this one is equal to 1, right? So we have to take the transfer function and do the inverse Laplace transform. So we have already done this exercise of completing the squares, and you can rewrite it like this, and you see that this is the Laplace transform of a sine that is damped by this type of signal. And to see see that you use the frequency shifting property. So this is the impulse response of our oscillatory system, and we can have a look at what it looks like in the time domain for different values of zeta. Okay, so this is the response for a small value of zeta, and here for a large value of zeta. And of course, if the damping ratio increases, well, you kind of see what you expect. You can also have a look at the step response, and if you compute the step response, well, you know that x of s will be 1 over s, so you multiply your transfer function with 1 over s, and this is what you obtain. And you're all experts in computing inverse Laplace transform, so you know that you have to kind of rewrite this using a partial fractional expansion. I haven't put the details, but it's something that you can do pretty easily. And then I have rewritten it here because I want to make sure that I have two terms that are appearing here. This is the Laplace transform of a damped cosine, right? And this is the Laplace transform of a damped sine. Okay, so this is the expression that we had obtained, and if you do now the inverse Laplace transform, you obtain this expression. And this is how a step response of a harmonic oscillator looks like for different values of the damping ratio. Well, it might also be interesting to determine parameters from your oscillatory system experimentally, and we're looking for ways to compute omega n and zeta, right? So if you do a step response, an experimental step response, you obtain something like that, and you can extract t, which is the distance in time between two successive peaks, and then you can also look at the values of the peaks with respect to the steady state solution. Here we have the value of the first peak and the second peak, but you could even look further in time and get, for instance, the value of the peak that corresponds to the kth peak. Well, using these values or these peak values, you can compute what is called the decay ratio, and the decay ratio is the ratio of two successive peaks, right? Decay ratio, and using the decay ratio you can compute using the logarithmic function what is called the logarithmic decrement, right? It's possible to construct the decay ratio and the logarithmic decrement using y max 1 and y max 2, but it's also possible to construct these values using peaks that are further down in time. Well, you can see that this period t is of course related to the damped frequency, okay, and this damped frequency can be rewritten as this thing here. So you obtain a relation between t, the period, and the parameters that you're looking for, zeta and omega n, right? Remember that there's a decay in the responses, okay? There is a decay of e to the minus sigma t in the step response. So by looking at this logarithmic decay ratio, also this logarithmic decrement, it can be computed that this logarithmic decrement is equal to zeta omega n t. You replace t by the expression that you have got over there, and you have a value of the logarithmic decrement, and you see that it's only depending on zeta. So now you can take this formula and turn it around, and you obtain zeta as a function of the logarithmic decrement. Okay, so it's just a matter of looking at the response, the step response, for instance. Look at the successive peaks, compute the logarithmic decrement, and then you obtain a value of zeta. Once you have the value of zeta, you can use it to compute omega n. And this leads you to this formula here, where you have to plug in this thing in here, and t, the period, is obtained experimentally. Okay, let's have a look at the frequency response of our second order oscillatory system. And for that, we look at the steady state response to a sinusoidal input at a given frequency omega, right? We know that the steady state response is this thing here. And a word of caution, steady state response, it means that you have to wait until all transients have disappeared. Well, the steady state response is also a sine at the same frequency. This is by linearity, but it is amplified and there is a phase shift, right? And to obtain the amplification, what you do, well, you need to take the transfer function, you replace s by j omega, you obtain a complex quantity, and if you take the magnitude of modulus, you can kind of see how much amplification you have at this particular frequency. You can do something similar with this complex quantity and compute the argument, and then you obtain the phase shift as a function of omega. So we see that this linear filter acts as a frequency filter. When you vary omega from 0 to infinity, right, you can kind of see how much amplification and shift that you're going to have, phase shift that you're going to have at that particular frequency. And this is often represented graphically, right, in a Bode diagram. And this is, of course, what we're going to do for this second order oscillatory system. Well, we are going to look now at the Bode diagram of a second order oscillatory system. The easiest thing to do is to rewrite the system like this. So we have divided numerator and denominator by omega n squared. And we're going to look at two limiting situations: omega much smaller than omega n and omega much larger than omega n being the natural frequency. Okay, let's look at the first example. Remember that we have to replace s by j omega. We obtain then a complex number, and we have to consider the modulus and the argument. Let's consider the case where omega is really small with respect to the natural frequency, and then you will see that these terms here will be very small, and you obtain an approximation of this transfer function. So you know that at low frequencies the transfer function is approximately 1, which means that the amplification is around 1 and the phase shift is around 0. Let's look now at the case where the frequency is much higher than the natural frequency. Okay, we know again that s is equal to j omega. If you square on both sides, you have this relation over here. Okay, now since omega is much larger than omega n, well, we can cross out this term and this term, and since s squared is approximately minus omega square, we obtain this kind of relation. Okay, so at high frequency an input sinusoid is more and more attenuated, because you see that you divide here by something that is big, and the minus sign shows you that the phase shift tends to be minus 180 degrees. Here, the fact that we divide by omega square here, if you work with a Bode plot, you know that in the y-axis you use dBs, and you have also a log scale for the frequencies. Well, you see that the slope here will be minus 40 dBs per decade. So we've looked at high frequencies, low frequencies. When compared with the natural frequency, what you can do obviously is also look at the natural frequency. So we'll consider that omega is equal to omega n. Okay, so we replace s by j omega. This time it will be j omega n. We square and we'll have s square is equal to minus omega n square, right? So at the natural frequency you have minus 1 over here and 1 over here, so these two terms, they compensate each other. You can replace this one by j omega n. Okay, so this one and this one will compensate, and then you have that the transfer function at the natural frequency is given by this quantity. 1 over j is equal to minus j. Okay, this you remember from your course on complex calculus. So you obtain this quantity, and what you see here is that, well, there will be amplification, and there will be an amplification that will grow when zeta, the damping factor, is getting small. Okay, and in any case what you'll have is a phase shift of minus 90 degrees. Okay, so this is the frequency response of our second order oscillatory system. So indeed you see that when the frequency is small with respect to the natural frequency, that the gain is approximately 1 or 0 dB, and that there is little or no phase shift, and this is indeed what you see on this side of the Bode diagram. When you consider that omega is larger, much larger than the natural frequency, you see that indeed the phase shift tends to minus 180 degrees, and that you have a slope of minus 40 dBs per decade. Okay, so your input sinusoid will get attenuated more and more when your frequency is increasing. So we can look here at the natural frequency, which is 1, what is happening, and indeed you see that the phase shift is minus 90 degrees, and you see that when zeta here is decreasing, well, you have more and more amplification. Okay, what we'll often do in the remaining part of the course is that we'll work with a normalized frequency R, which is the frequency that you're considered divided by the natural frequency. So you start with your transfer function, you replace S by j omega. This is what you obtain, and here you see the quantity R squared and R popping up, so you can rewrite things like that. You know from complex calculus that you can multiply numerator denominator by the complex conjugate of this one here, and you obtain this quantity. This allows you to compute the magnitude or modulus as a function of R, and the phase shift or argument as a function of R. One last thing, well, it might come as a surprise, but the peak value in the Bode diagram does not come at omega n or at the damped frequency, but it comes at another frequency which we called, well, the peak frequency, right? How can we see this? Well, we take our modulus of p that we've rewritten as a function of the normalized frequency R, and we take the derivative with respect to R. It's not that difficult to compute, but you'll see that it gives you this quantity, and you're looking for the R that is going to make this 0. You see here that the two R's over here will disappear, and this will be 0 if this thing here is equal to 0. So provided that zeta is smaller than this limiting value, which you can also write as square root 2 over 2, this will have a real solution, okay, and you can compute that solution to be r is equal to the square root of 1 minus 2z squared, right? And don't forget that r is omega over omega n, so we can compute the frequency at which this quantity PR modulus peaks, right? And if you plug it in here, you can actually compute the peak magnitude, which is given by this quantity here.